ladies and gentlemen, class recording has indeed started. So, all right.
Thanks, Morgan.
Over the past week.
What'd you say?
I did say class recording has started. Just,
What did he say?
Oh yeah, that was on the mic too.
all right. So, up on the board is a simulator that allows us to take a look at the different aspects of projectile motion. So, last week when we first started talking about projectile motion, we started with something like this, where this cannon is up here on top of a ledge, okay, and setting the angle of the cannon at 0 degrees, meaning that it's right along the x-axis of this frame of reference that we set up, right? And so if we fire this cannonball off of here, right, boom, like that, okay, that at the moment it became a projectile, it was moving horizontally, but the instant after it gets fired, gravity starts acting on it, and it goes down in this curved path, right? We said this was parabolic. In this case, it's only half of a parabola because it's starting up at the top. But we talked about the idea that when this is going on, right, the initial velocity in the vertical direction was equal to 0, right? Because it was traveling all horizontally and no vertically. So let me grab this real quick and just to make sure we look this, okay, right? And so we said here that in this case, VI in the vertical direction was equal to 0 because when it was shot, it was traveling all horizontally. Right? Good there?
Look at the guy.
Yeah, that's a statue. That's David. All right.
Yes.
So
With pants on.
with pants on, yeah, he's got boxers on. But don't worry, that won't last long. So
Oh.
throwing it out there. Pay attention. All right. So that was last week at the beginning of the week. And then on Friday, we changed it up a little bit. And we brought this cannon back down here. Okay? But
Oh no.
now, relax. But now, right, we set this cannon up like this, where it wasn't shooting horizontally now, it was shooting at an angle. And I just, picked 45 degrees for a reason that we'll see here in a little bit. But, so now I take this cannon, right, I've set my cannon to shoot this cannonball at 13 meters per second at an angle of 45 degrees. We shoot it off, boom, goes like this, and yay, we hit the target. Not that I was trying to do that, it just happened, okay? But, let's zoom in and go any further, okay. If we take this picture, okay, on Friday we talked about the idea that shooting this cannon off at 45 degrees means that this is what the initial velocity looks like, okay? But if the initial velocity is like that, it was really doing two things at the moment that it was shot off. It was really moving both horizontally and vertically, okay? And on Friday, we sort of worked backwards, and based on how far that projectile went and how long it took the projectile to get there, we sort of back calculated, and we figured out that at the very moment we could tell what the horizontal velocity was, but then also what the initial velocity vertical was, right? And that's kind of what we did on Friday. Yes? Does that sound familiar? This distance that goes, let's use yellow, see if that works out. This distance that goes from here to here, okay? Now, in this case, I'm going to cut this off right at this point because this is the x-axis, right? That's the x-axis of our reference. And so we talked about the golf ball that we were talking about just landed right where we shot it from. So I'm going to cut it off right there. But we refer to this distance as the range or the horizontal range. So when it asks you to calculate the range of a projectile, it's really asking you to calculate a horizontal distance. Meaning, on our chart, what will we probably be solving for? delta x, or if we say that x initial is 0, that means that really we were going to solve for what? X final, right? If we're solving for x final, that's going to give us the range of this projectile's flight. Okay? Does that make sense? Now, let's look at this a little closer. Okay, so there is our range based on a 45-degree launch. Okay? I am going to change the launch angle. First, I'm going to get rid of that blue line. I'm going to change this launch angle from 45 degrees to 60 degrees. We can probably make an educated guess about what's going to happen here, right? If we look at the flight of this cannonball versus the previous cannonball, what are we probably going to see? It's going to go shorter, but it's going to go higher, right? Boom, right? And there it goes. Okay? So that's 60 degrees. If we take and make this angle even greater and make it 75 degrees, what are we probably going to see there as well? Even higher, but even shorter. Okay? Now keep in mind, right? The whole time we've been doing this, we have been launching it with a speed of 13 meters per second. So it's going just as fast each time, but the angle at which we shoot it makes a big difference as far as its horizontal range. Okay? Good so far? All right. So this was our original launch angle was 45, and we went to a greater angle. But we can also go shorter, right? So there's 30 degrees. It's obviously not going to go as high, but if we look at how far it goes, okay, boom, there's 30 degrees, and it lands there, okay? So it hit the target, but did it go as far as when we originally launched it at 45? It didn't. And then we'll go down even farther, 15 degrees, right? Notice Statue of David in the flight path of the cannonball, right? When we shoot that one off, boom, right?
Oh, God.
Blew his shorts right off, okay? But he's still, he's still decent. Right? He's got a fig leaf on, okay? But more importantly to this discussion, right? I'm going to take a look, and I'm going to grab this picture from here over to here. Sam, we kept it, it's PG. I mean, so taking a look at these landing positions, this was the original one that we shot off at 45 degrees. Okay. This was 60 degrees, and this was 30 degrees. Okay? First, 60 and 30 add up to what? 90, right? But we see with those two angles, right? While the flight time is different, what are we seeing about the range? Same range, okay? And if we go 75 degrees versus 15 degrees, right? Again, 75, 15 add us up to what? 90. Flight time is different, but horizontal range is the same. Okay? So, moral of this story, any two angles that add up to 90 will get us different flight times, but the same range. Okay? But the maximum range will come if we shoot this projectile at an angle of 45 degrees. Keeping in mind, all of the initial velocities here were all exactly the same. We just shot them at different angles. Okay? Good there? So, to wrap up this discussion, range, right? Range is a horizontal distance. How far from the launching place did this projectile land? And then we see a pattern develops that as the angle increases, range gets bigger until we get to 45, but once we get past 45, range gets smaller. Okay? Good there? That being the case, let's take a look on your sheets. The last problem that we didn't do on Friday was number 47. It says calculate the maximum range of the golf ball in 4.12. So we just discussed first, right? We didn't just discuss this, but first, right? Let's get ourselves our list. Initial position, final position, initial velocity, final velocity, acceleration, time. Okay? And we said that if we're looking for maximum range, that means we're going to solve for what in this chart?
X final? Why?
That's because that's range, right? Okay, we said that going back here, range is a horizontal distance, right? How far does it travel horizontally? So that means if we're going to solve for range, we got to solve for a horizontal distance, and that's xf, right? Assuming, of course, that we call x initial 0 and y initial 0, right? That being the origin of our frame of reference. Okay? Good there? So that's what we're looking for here, right? One other thing though, right? In this picture that I gave you, the launch angle was at 54 degrees. Is that going to give us maximum range though? We just talked about that in order to give us maximum range, what does theta have to be? What does the launch angle have to be to give us the maximum range? 45, all right? So we need to change that, and that's going to change some of the numbers in our chart a little bit, okay? First, we can fill in this, and we can fill in this, okay? Good there? And then, using some information from Friday, I apologize, I should have had this up already, but on Friday, we calculated that that golf ball was originally hit at 13.6 meters per second. Remember, we figured out the initial horizontal velocity, the initial vertical velocity, then we used Pythagorean theorem to find the actual initial velocity. Does that sound familiar from what we did Friday? Okay. So Friday, we had a launch speed of 13.6, and that came because we launched it horizontally at 7.95 and vertically at 11. And we did Pythagorean theorem and got this to be 13.6. Good? But remember, that was when we had a 54-degree angle. We have to change this now, right? This is still going to be 13.6, but we need to take this angle and make it more like that. Okay? This is 13.6 still, but now we want to make this 45. What's that going to do to the x component? The x component is going to get bigger because we made it closer to the x-axis. But what's that going to do to the y component?
Shorter.
Make it shorter. It's going to make it smaller.
Maybe bigger.
In this case, yeah, because
45.
it's a 45, 45, 90 triangle, right? We remember, what do we know about 45, 45, 90 triangles? The two legs.
Same.
They have to be the same. Do we have enough information to calculate either one of these legs?
Mhm.
We do, right? We can use our trig functions to find out actually either one of those, right? But we really only have to do one calculation here because they're both the same, right? let's figure out what either one or both of those sides are. And if I remember right, I think it's 9.62.
Yeah, that's right.
Does that sound right?
The answer is 6.1.
No, 616. Yeah, we'll round it to 9.62. All right. Now, what do we do with that? Okay. Those numbers, remember, this 13.6 only applies at the moment that we hit that golf ball. Meaning, this is the initial velocity. But it's not initial velocity horizontal or vertical, it's the combination of the two. But now that we find these two legs, this is going to be our x initial velocity, and this is going to be our y initial velocity. Anytime I give you the hypotenuse and ask you to find the two sides, those are going to be the initial velocities, both x and y. So we can fill in this as 9.62, and we can fill in this as 9.62. One more thing in our chart that we can fill in before we start solving for what we need to solve for. We said that this is where the golf ball starts at 0, 0. We're trying to find out how far it travels on the x-axis. Where does it end up on the y-axis? It ends up back at 0 on the y-axis, because it ends up just as high as it started from. Good there. So, we go and take this trusty equation that we've been using all along, right? Right? And we can use that equation to solve for xf. Except, we're missing some information, right? We don't know the time. This is still an unknown. But we said we have a way to deal with that, right? If we don't know the time horizontal, what can we do?
The time vertically.
Find it vertically, right? Because these two times have to be the same. So using that same equation, except the y version of it, or the vertical version of it, right? Ooh, x initial, y initial. You have enough information to solve this equation for time. And then when we solve that equation for time, we can use that time to solve for x final. Okay? So I'm going to do that up here on the board because some people got a little bit confused with the math. So go ahead, just keep working on it. If you need help, look up on the board. Everybody okay what I did with that that algebra? How I got to where I needed to get to? Remember, if you've got in this step here, if you've got t squared on one side and t on the other side, we can just divide both sides by t, and that'll get rid of t on the right-hand side, but it'll only leave you with one t on the left-hand side, and then you can solve. Then, if you know t on the vertical side, then you automatically know it on the horizontal side. And then it's just a matter of using this equation, which is actually becomes pretty easy on the vertical side or the horizontal side because there's lots of zeros. You should end up with 18.9 for X final. Good there? Alright, so the one change that we made to this problem from the previous problem was this idea that first, maximum range means that we're going to have to change the angle from whatever it was to begin with to 45. And then, to start off the problem, we knew how fast it was going, and we knew the angle that it was going, and that allowed us to calculate the initial velocities on the x-axis and the y-axis. Okay. So, to finish that up, in your book, on page 190, or sorry, not page 190, page 140, number 41 and 42 are examples that are similar to the ones that we just did. I will put them up here on the board real quick, and then I will write the answers so you know where to go here, okay? And then we can take the next, you have about 15 minutes left. We can work on those in class and hopefully get to where you need to get to. If you need help, I'll be around, okay? On the calendar, right? Lots of questions that deal with the angle launch of the horizontal or of the projectile motion. Answers are down here at the bottom, right? So you can check it out tonight. Those are things that would definitely serve good preparation for the quiz scheduled for tomorrow. Okay? All right. I'll put those problems up, and then I'll post the answers so you can see what you're looking for. Yeah, it's 138. Sorry, page 138. My bad.
Over 2.
Because I had to close this down right before you guys came because my computer was acting funny, and so I had it up, and then yeah, there it is. So on page 138. We did problem number 40 on Friday. That was one of the examples that we did in class on Friday. So if you do 41 and 42, those will serve as good practice for the quiz tomorrow. Okay? Very similar to the problems that we did on Friday and today. So I'll get you started so you at least know what you're looking for. talk to somebody about problem, feel free. So up on the board, you got the answers for the two parts, right? X final, Y final for number 41, and then V final X and V final Y for number 42.